Today's lecture is about the calorie. So what is a calorie? It can be a little bit confusing. The podcast talked about it, defined it, but didn't really go into the confusing aspect of the definition of a calorie. And so that's what I'm going to cover today. The podcast sort of got some of the other interesting aspects of it. But we have scientists versus nutritionists. And here's Beaker. I don't know. These guys were near and dear to my heart when I was young, and probably way too young for this yourselves. But maybe you know the Muppets. Here's the scientist Meeker, and he says, or Beaker, he says 1 calorie, and he's using a little c calorie, 1 calorie equals 4.184 joules. Okay, and we'll talk about what a joule is in a while. And the Swedish chef is, no, borka borka. 1 calorie with a big C equals 4,184 joules. All right, so this is, in a nutshell, the confusing bit. All right, so 1 big calorie, or they call it a kcal, and we'll which is a big G, a big C calorie, getting myself tongue-tied, is equal to 1,000 small c calories. And when scientists talk about 1,000 small c calories, they call it a kilocal or a kcal. All right. So scientists will talk either when they talk about calories, they're talking about small c, or the kcals, the kilocalories, kilo referring to 1,000. It's the SI unit prefix for 1,000. Whereas nutritionists use the big C. Okay. All right, so here is the history of the calorie. And the podcast talked about this guy a little bit, Santorio. Pretty easy name when your first and last are the same. The guy, as they indicated in that podcast, was pretty obsessive compulsive. He was amazing. He measured everything he ate. He kept copious records detailing. So the daily logs that I'm getting you guys to take, he went to the nth degree. Just be glad I'm not having you measure your feces and urine every day. That's what this guy was all about. He was keeping track of all the food he ate and all of the food that was eliminated from his body. In fact, he went so far as to eat his meals on this strange contraption that you see in the middle there, this chair that was essentially a scale that kept track of his mass as he consumed the food that he ate. So he knew how much food he had consumed. That was how he did it. Instead of measuring ahead of time and then eating it, he would just eat what he wanted and then measure the difference in his weight. And this was all described in this textbook, Stetica Medicina. And another thing that was kind of interesting that he did, he invented the clinical thermometer. So he not only was he measuring the food that he ate and excreted, but he was trying to measure body temperature. And the first thermometer was invented by him. And so what it was is there's this big bulb that you see at the top there, and you'd stick this giant glass bulb in your mouth, and you'd heat it up, and it would change the ideal gas law. Are there any Woodsman Club people in here? You're a woodsman? Yeah, PV equals nRT. So it would change the temperature in the thermometer, and it would give these readings as to body temperature. So he was thinking about how the body utilized its food, how it burned its food. He didn't really think about it using the word burn, but he was thinking about temperature and food consumption and excretion, the net flux through the body. He was the first person that went about it in a sort of rigorous way, making these measurements in a detailed, systematic fashion. Enter Antoine Lavoisier a couple hundred years later. Lavoisier is just a fascinating individual. He's a really fascinating individual. So he was a French scientist, and I don't have a picture of him and his wife up here, but his wife helped him, Marie Lavoisier, Madame Marie Lavoisier. He discovered a lot of things. He, for example, named oxygen he identified carbon as an element, but in the context of the calorie, oh, come on, stop, go away. I don't know what that is. He built the first real calorimeter, and he was the first to describe combustion as well. So in this calorimeter that he has, he's got a guinea pig contained within this sealed chamber, and the chamber is surrounded by ice, right? And he would keep it, there was a control where it was at a certain temperature in the room, and he'd measure how much water dripped out over a certain period of time from the ice that was melting. And then he chucked this guinea pig in there, and he compared it to how much more water melted out of the bottom of his calorimeter due to the heat generated by the chilly guinea pig that was wondering what was going on in there. Unfortunately, Lavoisier was put to death by decapitation during the French Revolution, which is the grisly picture depicted in the middle. But he was a pretty interesting character. So part of his description and depiction of combustion, which is going to lead us directly into the metabolism of the human body, he discovered that diamonds combust. Maybe I have a picture of it in an upcoming lecture, or maybe it's some other class, but he used a magnifying glass that would have been as big around in circumference as this classroom, a giant magnifying glass with a secondary compound magnifying glass behind it, and goggles, the whole bit, focusing all that light down on a diamond. And he actually burned a diamond and showed that diamonds are made pretty much exclusively of carbon, and that the only gas they gave off was carbon dioxide when they burned. So Lavoisier. Yeah.
Question: isn't that ice calorimeter also going to take in heat from the surrounding?
Come again, louder.
Isn't that thing going to take in heat from the surrounding too?
Yeah, absolutely. Which is why he controlled it, right? He measured the amount of water that was eluted without the guinea pig, and compared it to the one that had the guinea pig, and so it was a difference. He was looking at the difference between the two. Make sense? Yeah. All right. So the big C calorie, or the kilocalorie, that we find on U.S. food labels, the Swedish chef's calorie, not Beaker's, it's essentially identical to the one that was first proposed by a guy named Nicolas Clement in some lectures that he gave about heat engines in Paris. And I don't have a picture of Nicolas Clement. I guess he was not wealthy enough, or I don't know, concerned enough about getting a oil painting selfie, but that's where he's buried, right there. In Père Lachaise Cemetery in Paris. He was pals with this guy named Sadi Carnot. And Sadi Carnot was a young man who went into the military and was actually not as interested in logistics and tactics and strategies of warfare as he was really in engineering. He was an engineer. And they became friends and discussed ways of defining energy, heat energy. And so this was all centered around the mechanical work, the mechanical equivalent of heat that a steam engine could do. So here is a picture of one of the steam engines that they devised and trying to describe how much work a certain amount of heat energy could produce in terms of moving a mass, maybe a train car or something, along a track. And all this work was conducted in Paris at this Conservatoire des Arts et Métiers that you see there in the center picture. Sadi Carnot went on to write quite a bit about thermodynamics and is considered to be the first true thermodynamicist. All right. So this definition by Nicolas Clement made its way into a famous physics text that was written by a guy named Adolphe Guénaud that got translated into English in 1863, as you see here. This is the first time the definition of the big C calorie came into the English language. Now, I haven't given it to you yet for good reason. We'll get to it in a moment. What is it? Here it is. You keep talking about it. I want to know. What is a calorie? What did he say? Well, one big C calorie, the calorie that you are familiar with on the box of Cheerios that you eat in the morning, equals 1,000 calories, equals 1 kcal, equals 4.186 kilojoules. I don't really know what any of that means. Hey, is that what you're saying? Well, it's the amount of heat needed to raise the temperature of 1 kilogram of water from 0 to 1 degree Celsius. Okay? That's the definition of the current definition of a big C calorie. All right. So no, I'm sorry. That was the definition proposed by Clement, and this definition found its way into popular scientific literature, such as an article called "The History of the Calorie in Nutrition," and this is when they first. The use of the term first came into a nutritional context. This was in 1863. This is the same year as Abraham Lincoln freed the slaves, just to help you get a sense of the time frame of all of this. Yeah?
I think in the gastropod podcast, they said that it was raising the temperature from 14.5 degrees to 15.5 degrees at sea level.
Yeah. So that is a current definition. I believe Nicolas Clement it was just going from 0 to 1. He was taking just melted ice and raising it 1 degree centigrade. And I don't know if he standardized it by elevation, because I'm not sure he fully appreciated the potential effect of pressure on that. That's my that's how I'd explain that. So here's the original definition that Clement used in Le Producteur, published in 1825. And then here, about 60 years later, is the definition that has, at this point, entered into the Imperial Dictionary in the English language. So they say, in physics, the quantity of heat necessary to raise the temperature of a kilogram of water 1 degree centigrade. It's the French conventional unit used in calorimetry. So they don't actually define it especially well there, do they? It came out of the realm of the specialists and came into the realm of everyday food consciousness in 1887, thanks to this guy, Wilbur Olin Atwater. And so they talked about Atwater in the podcast, and they talked about Atwater values and the amazing work that this guy Atwater did with measuring the caloric content of like 4,000 different foods. So, yeah, we can see here that he's relating a calorie to a different unit of energy, the foot ton. So he said 1 calorie equals about 1.5 foot tons. And then he went on to describe the caloric content in various pure food types. So I've talked about the 3 general food categories in passing. We're going to get into them in detail. Proteins, fats, and carbohydrates. He described them as having 4, 9, and 4 calories each. So on the left-hand side are the estimates of the energy density of those different foods that you guys told me about on the first day on that quiz. Remember, I gave you that first quiz and I asked you to tell me how many calories you thought were in food of various sorts, protein, carbs, and fats. You did pretty well. You did pretty well. There was one person in the class who was way, 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 way above, and there was one person in class who was way, way, way below, so they kind of canceled each other out, and everybody else was pretty much in the ballpark. You did a pretty good job of recognizing that fats are more energy dense than proteins and carbohydrates. And in fact, it's hard to know, as they alluded to in the gastropod, what the actual calories gleaned from protein, fat, and carbohydrates are going to be from person to person. So within the realm of error, you guys are probably just as right as the values that Atwater has. But the values that Atwater has, 494, are the ones that are in every standard biochem lab that you will see in most colleges. This is the number that they would use when calculating caloric content. All right. So here is a timeline comparing the use of the calorie, big C calorie, the kilogram basis, or kcal calorie, to the gcal, the lowercase calorie, the scientific calorie, and the joule. So Clement, as we said, was the first one to describe a calorie. That happened in 1825 with the big C. And then the small c calorie was first described, the one that scientists would use, by Fave and Silberman in 1852, about 25 years later. Also in France, I'm not going to go into that into detail. In about 1888, there was, so 1875, they had this thing called the metric convention in Paris, where they established what the metric system was, right? Everybody got together and they said, we need one unit, one set of units that are standardized, and they did that at the metric convention, and then about 13 years later, they developed the joule. And the joule is a kilogram meter squared per second squared. There's a lot of different ways, depending upon the application of a joule, to describe what it is. So taking a kilogram, distributing it across a square meter, and then moving that in time, accelerating that in time because it's seconds squared across a distance. All right, so that's a certain amount of energy, and that got codified into the System International, which is the current foundation of scientific measurement, which happened in 1948. All right. So last slide here. What is a joule or a calorie? Really, what does it mean? So here are some examples of a joule versus a big C calorie on the back of your cereal box. 1 joule in everyday life represents the heat required to raise the temperature of 1 gram of water by 0.24 degrees C. Okay, got that. Something a little bit more concrete. It's the energy that you need to lift a tomato, medium-sized tomato, 100 grams, 1 meter vertical from the surface of the earth. So there's a tomato, pick it up, stick it in your pocket. And it's the same amount of energy that would be released if you took that tomato and dropped it on the ground. Whatever tomato sauce would be made by dropping that tomato, that energy would be equivalent to a joule. What are some other ones? Energy released when typical energy released by heat of a person at rest every 1/60th of a second, every 17 milliseconds, approximately the blink of an eye. Approximately the blink of an eye, your body is burning a joule, just sitting there, being the beings you are. You can light an LED for 1 second, approximately, with a joule. So there gives you a little bit of an idea of what a joule is. On the other hand, a calorie, they're bigger. It's bigger. The heat required to raise the temperature of 1 kilogram of water by 1 degree C, right? The energy required to lift a beach ball-sized boulder 1 meter vertically. Please lift with your legs from the surface of the earth. It's the same amount of energy that would be released if you dropped the boulder on your toe. Maybe a little more energy as you scream bloody murder. Typical energy released as heat by a person at rest every 70 seconds. So a little over a minute of sitting there, just being, not doing anything, not even thinking, moving, just sitting there in a dark room, doing nothing. You're burning a calorie. So, and you can light up an LED for a little over an hour with 1 calorie, right? So there, what is that, 100 LEDs maybe? That was 100 calories. What did I do? Come on. All right, so that's a wrap.